Yeah, I think now I am able to write. So today we will be talking about the boosting. Okay. So just to give a brief overview into the same, see, we call something as ensemble models. So these models, they are actually not algorithms in their own right, right? But some kind of a mechanism that is applied on a specific algorithm, right? Some kind of a mechanism or some kind of a process that is typically applied on a specific algorithm. So to a large extent, these ensemble models, they fall into two main categories, though we can say three also. One is called as bagging. The other one is called as boosting. The other one is actually called as stacking. So what happens is, these are the three mechanisms that are applied on existing algorithms. So these are not new algorithms. These are the mechanisms that are applied. These are the computations that are applied on existing algorithms in a specified pattern, so that overall accuracy is improvised. That is the major objective. Overall accuracy will be improvised. Now, as we have seen in the last class, bagging is nothing but it's a bootstrap plus aggregation. So you bootstrap is you take subsets of the original data. That is what you are calling as a bootstrapping. And you apply different models on the different, you apply a model on the different subsets of the original data. What model you are applying? You are applying a simple decision tree kind of a model. You apply a simple decision tree model on the subsets of the original data. So you will get multiple results, right? Because instead of applying it on one single data, you are applying that on multiple subsets of the data. So which means instead of taking the decision based on a single decision tree, you might want to take a decision on few hundreds of decision trees. So it's like a collective decision making, right? So based on that collective decision making, we are aggregating all the results and finally saying that this is the probability that some person will default or some person will not default. So basically, what is that we are saying? We have split. We have parallelly applied a decision tree kind of a model to multiple subsets of the data, subsets of rows and columns. So you have applied parallelly a decision tree algorithm to multiple subsets of rows and columns. And finally, based on these multiple subsets that have got, it's a collective aggregated decision. Aggregate decision has been taken, and that is what is used for the prediction purpose. So in a random forest, what we typically observe is whatever the number of trees that we are growing, all the trees will grow parallelly. And each tree is independent of each other, right? So the collective decision may, so which means if I'm saying I'll grow 100 trees, all 100 trees are growing parallelly. So 100 different subsets of the data are considered. And for each subset, a decision tree is typically being plotted. And using that decision tree, prediction for the testing data element happens, and the collective. So there is a joint voting that can happen to decide whether this person will go towards the defaulters class or a non-defaulters class. So because the decision is taken based on the majority of 1,000 different trees or 1,000 different scenarios, it is observed that the accuracy of such kind of models can be slightly higher or better off, right? So that is the bagging way of ensembling. And of course, what we talked about, that ensembling technique is the most popular random forest. Random forest is the one that falls into that specific category. Then the second thing that we talk about is boosting. Boosting is something we haven't started. So this is also an assembly. But here, the major difference with respect to the bagging here is a sequential tree building process. Whereas in the bagging and random forests in particular, there is a parallel tree building process. Here you can see that the tree building process is sequential. So even this model, all the things that fall under boosting, you must have seen that there are so many boosting algorithms. One is called ADA boost, gradient boosting machines, right? Or we call extreme gradient boosting, light gradient boosting. So there are so many slight variations, but various boosting algorithms that are available. All of them, they implement a similar thing, but technically there are some differences in the way they handle this boosting mechanism. But all of them, their major target is improve the result over the decision tree. Decision tree is always like a single tree, which is deciding your outcome. So I want this to improve the decision tree process. And as I told you, just like bagging, boosting is also not a machine learning algorithm. It's a kind of process, or it's a kind of methodology that gets applied to the existing algorithm. And more predominantly, it gets applied to decision trees. Now, the way it's again a collective decision making. So probably if I have to look at the probability based on some variables X, the probability whether a particular person will default or not, you try to look at the decision of the T different trees that we are growing. Tree number 1 to tree number T, I can very well look at the individual decision that is coming. I can sum across all the decisions. But the only difference here is at any point in time, if I am looking at, let's say, the teeth tree, if I am looking at the teeth tree, right, because it's a sequential thing, it actually builds upon whatever is the tree. So this is the tree. If I am saying HX is the tree, teeth tree, or probably I like it, this is like, so HX is the teeth tree. So there would be some kind of a multiplier on the top of it. So which means there could be, so for the T minus 1 to tree, there could be a different learning rate, right? There could be a different learning rate. So basically what we are saying is this H of X is the ML algorithm, right? So most of the times you can think of them as a decision tree. So I am talking about the decision tree. So the teeth decision tree is giving me some specific output. I give an alpha T multiplier to that particular output, right? And then take it for the T plus 1's computation. So basically what we are saying, forget about, in case you are not getting into the mathematics, I'll again give you one more mathematical expression slightly later on. So we can very well say that here it is combining. So sigma means there is a combination. What is that combination that is happening? The combination is happening about the various estimators. So each estimator is coming in, one estimator is coming in one iteration. So each of these estimators, there is a combination. So there is a kind of an alpha factor that is acting as a multiplication, right? So this is what we can call as the coefficient. So this coefficient alpha, which changes with the tree, which is different for different trees, I'm combining all of them so that the intention is the overall estimate will become an effective estimate. So in a way, you can very well say any boosting that you are doing, it is like you are trying to solve an optimization problem, right? You want to minimize the overall error. So you are trying to look at the optimization function that is applied on the cost function. So the cost function is the error function. So basically you want to reduce your error by altering the weights that you would like to give to your different trees. By giving different weights to different trees, your end objective. So basically it's a simple problem, right? Rather than giving equal importance to all the trees that are grown, you are giving a differentiated weights to different trees so that the overall error is actually coming down. So that is the broader concept that you can think of. Rather than giving equal weights to all the trees, which is what happens in your random forest kind of algorithm, you are giving differentiated weights to the different estimators that are coming out at each of the stages so that the overall error rate is typically minimized. That is what is the concept of boosting in general. Now, this entire world of boosting started off with ADA boost kind of an algorithm, though not much used in the today's world, but we need to understand the concept. I mean, we need to understand it to understand the overall concept of boosting, right? So the concept is ensemble of weak learners. We will define what is a weak learner. ensemble of weak learners, and probably you are doing a kind of combining all these weak learners. So you are giving differentiated weights. So that is where I am calling it as a weighted average. I am giving differentiated weights to each of these learners. And so the weights are coming not randomly, but they are purely based on the adjusted values. These weights are primarily adjusted for the misclassifications that have happened. So what does that mean? So initially I may do my first iteration, first tree. I will look at those observations which are misclassified. So there could be, once I did this classification model, so some predictions could be correct, some predictions could be misclassified. So those observations which got misclassified, they will get a higher weightage in the next iteration. They will get a higher weightage in the next iteration. And like this, the process will keep continuing every time. So the tree is developed on a sequential basis. The weightage to each tree will keep changing. In the random forest, each observation has an equal chance of being included into the sample. Whereas here, you are seeing that more weightage is typically being given to the misclassified observations and lesser weightage is being given to correctly classified kind of observation. So it all starts off, so it's as good as saying, rather than having one expert, I'll have a few mediocre people. I will train them in the way I require, and I will try to extract the best output from those people. So that is what is the fundamental behind the boosting and the boosted tree. So here we are using the word weak learner. Why did we use this word weak learner? Normally we said in a tree, typically it goes like this, right? This is the way the typical tree is going to grow. Right? So the tree can have a good amount of depth. But which means the relationship of classification is better handled if my tree is growing a little bit deeper, 2 levels, 3 levels, 4 levels kind of a depth. So the tree is growing more deeper, then it looks like it is able to address the complexity that is present in the data. But to a large extent, so when I'm saying it's a weak learner, we only talk about trees of only 1 level deeper. That's it. This is what is my tree. So these trees are called weak learners, right? No complexity, only one variable in a tree, right? So these are actually called stumps. These are called stumps, and these are also called weak learners. So there is only one node, and probably these are leaf nodes. One node and a leaf node. So only one variable will be used for dividing the entire data. So that is called as a stump. Now what we say is, in this boosting algorithms, we aggregate multiple such weak learning models, allowing the ensemble model that we have considered, which is nothing but a combination of the various models. So that learns slowly from the feature. So this is one more important difference between the random forest and the boosting algorithm. So let me just see what is happening. I'll give you a very crude example. Let's say we talk about a two-dimensional data. Only two variables are there. Of course, we know that the boosting mechanism, it starts only with one variable at a time, right? Stump. So I will talk about some data points. Probably let me say that these different data points. So this is one category of data. Then probably I may have the other category, something like this. Right? Let's say we have a data like this. So now let's assume that we want to use a gradient boosting mechanism, or we want to use a simple boosting mechanism, which is what is called as a ADA boosting mechanism. Right? These are the different points. So probably we have five, let's say the circles denote not default and x's denote default. So we had two variables x1 and x2 where 10 customers are there, and this is what is the story for that. So just for as an example, so anyhow at any point in time, we will take only one variable at a time. So basically, let me quickly assume that, let's say I have drawn a line like this because only one variable. So x1 equal to something, x2 is anything, but x1 equal to some value. So this is how, let's say, we have drawn our first. So this is our first tree number 1. So which has gone based on x1. x1 less than some, let's say this is some p value. So this side we got x1 less than p, this side we got x1 greater than or equal to p. So here we got only two non-defaults, whereas here we got 5 defaults and 3 non-defaults. So we see that these 3, they are misclassified. These 3 got misclassified because of the first tree. We have built the first tree using some criteria. So with that, we found that 3 of them are misclassified. So this is my first FT. So this is F1 of X. This is the model that came out as the F1 of X. So then I know that these 3 are misclassified. So they will get a very high weightage now. They will get a higher weightage now. Now, which means which means their probabilities of being inclusive in the model, which means there is a kind of higher values that are being assigned to these. They are going to get a higher weightage. Now, with that, let's say in the second iteration, I may, let's say, want to redo this exercise. This time I would put a rule on x2 and k. So x2 greater than or equal to k, we'll find some set of values. Less than or equal, less than k, they'll find another set. So probably here I could see 4 circles are there, but 1 cross is also there. So looks like this guy got misclassified. And whereas this observation also got misclassified in the second iteration, because below this there are 4. So overall, when I'm doing my second tree, x2 greater than or equal to k less than k. So greater than or equal to k, I have 4 non-defaulters and 1 defaulter. less than k, I have 4 defaulters and 1 non-defaulter. So obviously now this observation and this observation are misclassified. Now in the third, so this is what will become my f2 of x. Now this f2 of x will typically take the input from f1, right? So basically what will happen here, my f2 of x will so f2 of x will come out based on my alpha, probably at time t plus 1. I am multiplying it with whatever the model that is coming at the time t plus 1, which is 2. So alpha 2 multiplied by h2 of x. So this is my second model. And probably the third time when I am implementing, let's say I am implementing this kind of a model. Again, I see some kind of negative kind of classification. But now you look at the good thing. In the same case, let's say I integrate all these three models, right? So my three models is, one is a line here, the second is a line here, the third is a line here. You look at now each box. This box is all non-defaulters. This box is all non-defaulters. This box is all defaulters. This box is all non-defaulters, defaulters, default. So you are seeing different boxes that have come up. They contain a clear distinction between the defaulters and the non-defaulters. Each box that came up. So initially they are only one variable at a time, but we had three such kind of tree models, three such weak tree models. Why weak? Only one variable is taken at a time. So that's the reason they are called weak learners. We combined these three weak learners, and based on that, we were able to do the prediction almost 100% accurate. So even if I draw any kind of a line or anything, it's not that easy to draw a line here, right? No straight line can be drawn which can separate my zeros and one. So this is where, if I'm having, now basically what has happened in the entire process is, if I'm looking at, right, the overall scenario, I'm taking whatever is my is my f at time t minus 1, and I am adding, if I am looking at whatever is the total function value at time t, I am taking the value at t minus 1. I am taking the alpha value, which is the correction, which is the learning rate at time t, and whatever is the model prediction that is coming out at time t. So this way the model is getting updated. So let's say if you are trying to work with different samples, so we have observations, n observations are there in the data, right? And for each one, let's say my outputs are y equal to 1 to n, y1, y2, yn. So here it's better that you take the output in the range of -1 or -1 and +1. So instead of zeros and ones, you can very well take as -1 and 1 for a better result. Now, initially what we are saying, initial weights, you can set all of them to be 1 by n. Because we had n observations, you can set for each observation. So you can set the overall weights to be 1 by n for each one. So you will set a kind of an error function here, the cost function or the error function, which will come out as e to the power minus yi. Yi will take a value either -1 or +1, and you take it as f of xi. So f of xi is nothing but for this particular model, multiplied whatever is the model prediction, multiply it with a learning rate. So that is what we are calling as your f of xi. Based on that, you will get the error function, right? So if you are taking any specific decision tree model, obviously we are going to build T trees altogether. Let's assume we are building T trees altogether. So in the first tree, you can very well choose what would be the variable that, or what would be the feature that would be used for splitting the tree. So that will become the first weak learner, right? So once so there my objective finally is try to look at this particular HT, whatever is the model, that will minimize the weighted sum of all the misclassification. So I want to choose whether I should choose my variable P1 or P2 or PK. That is completely dependent upon how many of them. So which particular variable has overall lower misclassification of the error. So based on that, you can very well, now this is what you can call it as your epsilon. Epsilon is what is the misclassification. So there could be 20% misclassification, 10% misclassification, something like that. So based on this misclassification, what the ADA boost model simply says is, once you know how much is your misclassification. So basically, let's say we have age, gender, and score, 3 variables. So you can very well try to find out what is the misclassification, what is the lowest misclassification that I am getting based on the age. What is the lowest misclassification that I am getting based on the gender? What is the lowest misclassification that I am getting based on the score? So whichever is having the lowest misclassification, let's say gender has the lowest misclassification after the first iteration, right? Probably let's say 10% is the misclassification that gender got, whereas 14% misclassification is what the age has given, and 16% misclassification is what the score has given. So let's say gender has the least misclassification altogether. So the learning rate alpha in this case is simply taken as the logarithm of 1 minus, this is what ADA boost has actually proposed. 1 minus, so basically this will become logarithm of 1 minus 0.1 divided by 0.1. So this comes out to be log 9, and that is what will be my alpha value. So that is the first step. So which means for the next step, the function would typically become, right? So when I'm applying this, so I'll take my previous. So I'm taking my previous trees value. I will take this alpha t, which has come out to be log 9 in this iteration, and I would consider whatever the model. So I will give a weightage of log 9. I'll give a weightage of log 9, and I would multiply it with the outcome that is coming out in the teeth process for every observation, right? So basically now we are getting different weights. So the weights are getting updated. So you update the weights. So basically for the next period, what is the weight that can come out for the next period? The weight, or for the next tree. So you take the current tree at time t and you multiply it with that error function, e to the power of y. So you have your alpha, which is what is your learning rate, and your model, the teeth decision tree model. So based on this, you will find out your new weight. Now these new weights may sum up. If I'm doing it like this, these new weights may be summing up greater than 1 or less than 1. So probably normalize them so that the sum of them will come to 1. So what is happening in the background, or probably without getting too much into the mathematics of each of them, probably you can go through the mathematics separately in case you are more interested. But what is typically happening is the weights are getting updated. Based on the weights are getting updated based on the misclassification that is happening in the previous tree. So the misclassified elements of the previous tree are getting more weight, and the ones that are correctly classified, they get a lesser weight in the next iteration. So, and accordingly, the weightage for each of them also, the weightage for the prediction for each of them also differs. And that weighted average is what is typically applied. So small differences, if you want to understand from a functionality perspective, these trees are not executed all at one time. Each tree is getting executed based on the results of the previous tree. So this is a typical algorithm called the ADA boost algorithm. Now but ADA boost to a large extent may not give that sophisticated result, right? So that is why, and probably it may take a lot more time for giving you the result as well. Now that is where the focus has moved towards an improvised version of boosting, which is called as a gradient boosting. So rather than using just percentage of misclassification, so that was what was used for determining my learning rate, for determining the error, etc., percentage of misclassification. Whereas here in the gradient boosting, this is also a sequential process, no doubt about it. But the way the sequence is built is different. So the sequence building process is different in case of gradient boosting. So first thing itself is there are no stumps here. So stumps are like weak learners we have already talked about, right? Only one single node and multiple leaf nodes. So here there is no stump kind of concept. So even you can grow large trees also. So weak learner, definitely it has slightly overcome the concept of weak learners. But here the most important thing is the training model keeps changing. The training model keeps changing. What is happening here is the errors of the previous model so this is the most important element. The errors of the previous model, they become the target values for the next model. Right? The errors of the previous model will become the target values of the next model. So that is what is happened. So basically, just to give you, let's say I say x1, x2, y. I'm just giving you some dummy numbers. 3, 4, 8, 6, 10, 7. Okay. Let's say the value of y is this. Let's say these are the values of y. Right? And just for the sake of argument, the tree model will take some predicted values, right? So the first tree, obviously, these will be my predictor variables, and this would be my target variable. Based on that, a decision tree will be built. So let's assume based on the decision tree, the predictions have come out something like this. Let's say these are the predicted values that have come. So obviously here I can take the error. So actual minus the predicted. Let's say these are the errors, right? 12 minus 10, actual minus predicted, 20 minus 22, 30 minus 27. So now what will happen in the second iteration? Let's say this will become my feature variables. Now this will become my target variable. This will become the target variable. Now again some prediction of this will come up. So let's say a new prediction has come out. All right. So let me just okay, let me say here the new prediction is this. Okay, so let me take I'll take some new prediction. Okay, some new predictions I'm making. Okay, so what would happen now? This is what has come out as the new prediction, right? So this new prediction E hat will be added to the existing prediction. So typically my new Y hat will become 10 plus 5 by 3. So probably it's like 55 by 3. 22 plus 1 by 3, 67 by 3. 27 plus 1, 28. Now again I can find out the new error. So 12 minus 55 by 3. So some error will come. So then similarly the other error. Now what will happen? This error will become the target variable. So like this, the process will keep continuing. The error process, the error will become the target variable value for the next iteration. So that's how the model keeps running, right? So basically what is happening? You initially get the predicted value. You calculate the residual or the error. Calculate the new model to predict the error. You take the error itself as the target variable and again predict the value of the error. So then add back that error to the previous predicted value. So sometimes you may want to add it in completion, or sometimes this error you will actually add some learning rate times this error prediction that you have got. Rather than adding all of them, you may want to put a kind of a learning rate and add back that error that you are getting. So this process keeps continuing. So what we say is when this continues for a few number of iterations, so different trees are being built, and what we generally find is this model will be more robust compared to a single tree kind of a model. So within this, so this is what is the gradient boosting kind of a mechanism. Gradient is what is the slope. The slope gets boosted because the slope of that error model is typically being considered for an updation of the process. So that is why this is called as a gradient boosting model. And generally, there are a few more variants like extreme gradient boosting. These are just a technical ways in which the same gradient boosting algorithm itself, but typically you could see that so some kind of additional aspects are there in terms of automated feature selection, extra randomization parameters. So some technical jargon come into picture in case of extreme gradient boosting. Similarly, we talk about light gradient boosting. So here, this is purely based on the leaf node rather than the branch nodes. So you can read through each of these technicalities, how differentiated, etc. Boosting as a mechanism. So let us see now. I think we have implemented a few models, so we'll have to see how the performance of each of them been, right? So if we really look at this problem, let us see which one has done the best. So random forest, if I'm predicting the model on the training data, the accuracy is 1. That is where there could be a very good scope for overfitting, right? Because when it performs on the testing data, its accuracy is hardly 84% or 85%. Whereas on the training data, it is 100%. Now that is where you should always look out for the testing data, and we have already talked about 5 different metrics that you would better prefer looking at, right? We have done the hyperparameter tuning. So here there are different hyperparameters. One is the criteria. We have already discussed in decision tree whether to use Gini or entropy. We have discussed both the criteria there. The maximum depth of the tree, the maximum number of features. So here, as we said, in a random forest, number of features can also be varied, square root of n. So here we have given different numbers based on the number of features. Number of samples that should be there, splitting the tree, and number of estimators. Estimators is primarily coming in terms of number of trees that you want to grow. Okay, I have switched off my video primarily under the premise that my voice was breaking. But can you just confirm if it is still happening? That too on a large scale. Okay. Just give me 1 sec. I think. Yeah, my internet is okay. Okay, I'll keep this window aside. So whenever it is fully breaking, please again put it in the message. Okay, so these are the 5 major hyperparameters that you can look out for random forest. So when I run this random forest, it looked like almost Okay, is it looking better now? Can someone confirm whether it is better? Okay, okay, fine. So when I'm looking at with the clearly coming out whether whether I'm maximizing the accuracy or balanced accuracy or area under the ROC curve, we are seeing that more or less, except for this criteria or probably this, we could see that number of estimators is 200 minimum sample, which is what is increasing your accuracy of the model. So when we went ahead and predicting the accuracy, we can do the same exercise for balanced accuracy as well. So we could see that the accuracy of the model has gone up to 85.39%. So we have discussed all these things in detail earlier. So you can even visualize the decision tree. You can get, so on what basis the rules are getting, what kind of rules are there for the splitting of the tree. And similarly, we have gone ahead for gradient boosting. Get on the training data, the accuracy is 88.96%. What has happened? So on the testing data, see that there is a slight decrease, right? And this is how the confusion matrix has come out. You know how to interpret that, etc. So then you can look at some similar kind of features with respect to hyperparameter tuning, maximum depth, maximum features, minimum samples, because it does not have its own algorithm. So it actually picks up from the decision tree itself, right? Primarily, you will talk about these two parameters, which are more and more specific to either random forest or gradient boosting. In gradient boosting, you have an additional variable called learning rate, because that talks about how much of the error prediction of the previous model of the previous tree should be added back to the previous estimate, right? So the current tree, whatever is the error prediction that has come out from the current tree, that error prediction is typically multiplied by a factor, which is what we call as a learning rate, and added back to the previous prediction value. So added back to the previous predicted value. So that's how the variable keeps getting improved. The estimate will keep getting improvised. And after a certain number of iterations where the estimate cannot be anywhere improved, in that case, the overall process will be stopped, and from there it keeps continuing. The overall process will be stopped at that point in time, and from there the final predictions are going to happen. That is where your model gets frozen. So because there are so many parameters here, right? 5 into 5 into 4, 100 into 5, 500 into 5, 2500 models have to be run. Obviously, it is going to take quite a good amount of time in this environment. So that's where I'm going for a randomized search. So randomly pick up 10 different, or I think I did not run this line. So I can say randomly pick up 10 different models out of this 2,500. So obviously it may not pick up anywhere good kind of a model. So we may not get the greatest output. So only 10 different models will be fitted here. So let it run. Okay. So the gradient boosting model is what 10 only we used only 10 randomized searches. So but under all the three criteria we got different best models looks like, right? Under the accuracy maximization, this was the best model that came out. Under the balanced accuracy maximization, this was the best. And under the area, under the ROC curve maximization, this was the best. So probably if I look at from a balanced accuracy perspective, right, we'll try all. So from a balanced accuracy maximization perspective, we could clearly see so you could see that 56% is the maximum balanced accuracy that could come. And in that case, the accuracy is only 83.82%. But when I am going for the accuracy maximization kind of a model, my accuracy might go up there. In that case, the accuracy has gone up to 85.89%. Balanced accuracy got a little bit down. So depending on what is our objective, now you could see we can compare these results with the random forest that we did earlier. The random forest model has generated 85.39. Whereas here we could see that the gradient boosting has generated 85.89% overall accuracy. And here we have gone for random search, right? Probably if you go with a grid search, you might still get a better result. But obviously that would be at the expense of the huge amount of time that goes into developing such a kind of a model. All right. So that's the thing. And similarly, XG boost also we have talked about. But the XG boost is not a part of is not a part of the scikit-learn library. So there is a separate package that is coming up, which is called as XGBoost itself. So we have classifier from this package called XGBoost. So again, here all using, right? So you can see gradient boosting. Boosting is just a kind of a mechanism over an existing ML algorithm. So you can have boosting over the top of decision tree. You can have boosting over the top of linear regression or any such kind of models as well. So here we are using a gradient boosting tree, 100 trees. The learning rate is what we are calling, this is represented as eta. So the learning rate is typically taken as 0.3. So these are all hyperparameters which we may have to tune later on. The maximum depth of the tree is 6. The gamma is again a kind of a factor which is actually used for pruning the trees. So if at all we get that information gain, right? We talked about entropy, and an information gain is nothing but the change in the entropy. When we discussed about decision trees, we talked about. So what we say is, whenever the gain is lesser than the gamma value, we will not further grow the tree. We will stop the tree there itself. That means the tree gets pruned there. So that is what is the gamma value. So here when I set a gamma of 0, it means that only when the gain goes negative, then only the tree will not be built. Otherwise, the tree will continue to be built. Then regularization parameters. Those regularization parameters also are very, so we have seen earlier 5 different, by default it would be 1, but we can very well set it to be 0.1 or 0.01 on the lower side, 10 and 100 on the higher side. Okay, and so these are some of the parameters that are associated with the gradient boosting model. You will fit the model. You will fit the model. And once the model is fit, we can very well predict it on the training data and the testing data. And we can find it on the, we can find the accuracy on the testing data. It looks like the accuracy is around 89.3. But when you run it on the training data, the accuracy can be much higher. So which means again, there is a possibility of overfit. And you can very well do a kind of hyperparameter tuning. So you have different eta values, which are your learning rates, the gamma values, which are where you are setting you are comparing the gain with the gamma, then the number of estimators. So we have already discussed about these various parameters. Because there are so many multiples, like here there are 5 or 6, here there are 5. So overall the number of models that you may be building is too high. So that's the reason you can very well go on your randomized search. And based on that, you can very well go ahead with the prediction. So just to see if the XGBoost, extreme gradient boosting, has performed slightly better off compared to that of the regular gradient boosting kind of an approach. So this look like the best parameters are you take a subsample of only one observation. One means so the entire 100%. Don't do a kind of subsetting of the data. Only 10 trees are right. We went from 1, 5, 10, 20, 40 and 100. So it shows that only 10 trees are sufficient. Minimum child weight, so which means the minimum number of observations that should be there in the child tree. Maximum depth of the tree is 5. The gamma is 0 and eta is 0.2. So with that, it looked like the best possible model has come. So if we look at it, the accuracy is around 85.8%, right? Probably the kappa score is slightly on the lower side, but definitely in a way to increase your accuracy, probably the other models also have registered similar layers of kappa itself. But yes, so you can very well run. But all the models are typically run in a similar kind of fashion. That is what you could typically see out here. Then on the similar notes, you have a few other mechanisms, right? Few other algorithms. Or if you have any queries on this boosting, probably we'll discuss by spending some time. Because the implementation is more or less similar. Krishna's perspective is more or less similar. But probably it got muted. So the practitioner's perspective is more or less similar. But probably if you want to understand some of the conceptual aspects, that is where probably we can spend some time on. Otherwise, I'll talk about the algorithm as well, which is what is called the naive-Bayes algorithm. So this is a slightly, this is into the fourth category of learning. We talked about 3 categories already. One is the error-based learning. Then we also talked about distance-based or similarity-based learning. We also talked about the information value-based learning. And the fourth one that we are now looking at is the probability-based learning. So naive-Bayes comes under the probability-based learning algorithm. So basically the name itself says it is based on the Bayes theorem. So if you remember the Bayes theorem, the probability of A given B is equal to the probability of B given A times probability of A divided by the probability of B. So in a way, this is like initial probability of A, probability of occurrence of A. So this is the reason it is called as a prior probability of occurrence of A. Then there is some new that got occurred called B. There's a new event. So basically, if I have to relate it to our examples, so initial probability of default. You can consider initial probability of default. So just by looking at the default column. Don't take any other features or variables. Look at only your target column, and based on that, you will definitely get your initial probability of default. Now, a new information has come. That information is one feature. You had one new information, which is what we can call it as one feature. So the feature could be your debt to income ratio. That is what is B. So a new feature has come. So first of all, what is the P of that particular new feature? But given the A, which means given default, what is the probability of that particular feature? What is the kind of debt to income ratio? Given that no default, what is the probability that the debt to income ratio is more than this or less than this? So that is what is probability of B given A. So this is what will come out as the likelihood function. And this one, so after this new event has come, what will be the updated probability of default? Updated probability of default, is it increasing or decreasing because of the new information that has arrived? So that is where this probability is called posterior probability. So again, the objective is to ensure that the probability is maximized. So that is where this is typically called as a probabilistic kind of a learning, right? So obviously you can use it in classification or regression problems, but to a large extent in natural language processing, where this is used for classification primarily, but it has a lot of applications in natural language processing, especially when there is a large high dimensional kind of a data. What is high dimensional data? You have more number of columns, and most of them are either are dummy variables which have a 0 or a 1 kind of a thing. Most of them will be binary in nature. So it's probably what we will say is this algorithm is one of the most simplest kind of an algorithm, but it is very, very effective. Sometimes it may not be as effective as random forests or gradient boosting, but definitely it is a very effective algorithm for classification, because one of the advantages is it actually builds fast. It does not consume large amount of time. It makes very fast calculations, which means the predictions are also done much faster. So sometimes what people in the industry do is, even if its accuracy is a little bit compromising, little bit, right? But because of the fastness of execution, they might still want to prefer this algorithm, especially for taking live decision, wherever real time decisions are required. There, this algorithm comes into picture more comfortably. So as I told you, this is a probability based learning. So the higher the probability of belonging to a group called default, so the decision would be that this person will default. And if the probability is lower, then obviously the final classification decision also is this person will not default, right? So typically in the text mining, there is a very, very important mechanism called sentiment analysis. So while doing that sentiment analysis, this kind of algorithm comes in more and more handy. Now, yes, okay, it is going with the Bayes theorem, no doubt about it. But why this word called naive? right? Naive actually as an English word, it is more like a crude, not sophisticated, right? That is what the English meaning for the word naive. Now, the reason is, let's say we talk about 3 feature variables and 1 target variable, right? So what are we saying here? The probability of y belonging to default given the values of x1, x2, x3. This is what is the problem, right? I want to find out what is the probability that the person will default given the 3 values x1, x2, x3. Now, if I go with the Bayes theorem, what will happen? This will become like probability of x1, x2, x3 given default multiplied by the initial prior probability of default divided by the probability of x1, x2, x3 coming together. So this part probably can be ignored. So all it is coming out because for all of them, the denominator is going to be common. So what is typically being said here is you will consider these independently. Probability of x1 given default multiplied by probability of x2 given default multiplied by probability of x3 given default times probability of default. Now, when can you do a multiplication of individual probabilities? Only when your x1, x2, x3, they are treated as independent. Then only you can do a multiplication of the probabilities simply. Right? Otherwise, see, this is like an intersection of x1, x2, x3. The intersection of x1, x2, x3 will be simply taken as the product of x1, x2, x3, probabilities of x1, x2, x3, only when these three probabilities are independent, 3 events are independent events. So all we are saying is the 3 variables that we have considered, they are independent variables. We did not check whether they are independent or not. We have simply assumed that they are independent and we are doing this entire exercise. So when the variables are really independent, probably this model will produce a very good realistic forecast. But when the events are very much away from independent, then this model will not produce appropriate forecast, as we have clearly seen out here. All right. So that is the reason we did not check. See, the point is we did not even check whether they are independent or not. We simply assumed to be independent. So that is where this is called as a very crude or naive kind of a model. But still it is used very heavily in the industry. So the occurrence of x1 is independent of the occurrence of x2. So these 2 events, they are independent. They can occur together, they may not occur together, they are independent. So there is no dependency between x1 and x2. So it's not like if x1 occurs, if x1 is high, not necessary that x2 will be higher, or not necessarily that x2 will be lower. There is no relationship between x1 and x2. So that is what is typically going in, right? So which means occurrence of one feature x1 is independent of the occurrence of the other feature x2. So each feature x1, x2, x3 separately and individually, they contribute to your identification of whether a person will default or not. So that's the reason I have separated their probabilities, because individually each feature can very well contribute. And obviously the Bayes as a word, we have already discussed the Bayes theorem, right? So probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. So all four. So the denominator, generally what we say, if I am talking about the probability of, let's say, x1, x2, x3, this is typically called as my marginal probability, or what is the probability that the new information will occur, right? And prior, we have talked about posterior and the likelihood. So probability of the new events x1, x2, x3, probability of them occurring given that the person has defaulted, or given the person has not defaulted. So we can typically look at, I think, so any data set, right? Probably we can think of some quick data set. And we can quickly, let me see if I have some other data set to work around. Okay, so let me try some age and sorry for the disturbance. Okay, so the age, and probably let's call it as default, right? So I can very well say probably greater than 50, yes. Then less than 30, yes. Probably 30 to 50, yes. I'm just taking some cases, 30 to 50, yes. Less than 30, no. Greater than 50, yes. Then we can talk about less than 30, yes. Greater than, so we are talking about one information now. 30 to 50, yes. Greater than 50, no. Less than 30, no. Less than 30, yes. Greater than 50, no. So let's say some such kind of observations we have taken, right? How many we have to 5, 6, 7, 8, 9, 10, 11, 12, let's say 30 to 50. Yes, I'll take another 30 to 50. Yes. So let's say overall we have 14 such kind of observations. Now, what we can very well say is the age wise, I can very well see how is the distribution of S's and how much is the distribution of no's. So we have someone who is less than 30, who is 30 to 50, and who is greater than 50. So in the less than 30, we have yes, yes, no, no, yes. So basically we have 3 yeses and 2 no's. Similarly, 30 to 50 looks like yes, yes, yes. All 5 are yeses. So we'll take this. And in the case of greater than 50, yes, yes, no, no. So 2 yeses and 2 no's are there. Let's say this is what we have based on the age, right? So now you can very well think about, let's say for this case, we will talk about kind of overall total probability. So what is the occurrence of 30 to 50? 5 by 14. What is the occurrence of less than 30? 5 by 14. What is the occurrence of greater than 50 age people? It is 4 by 40. And similarly, if I look at it this way, what is the occurrence of defaults occurring? 10 by 14. What is the probability of no defaults occurring? Which is 4 by 40. So now I can very well talk about the probability of default equal to yes. Given, right? Given, let's say the age is less than 30. The age of the person is less than 30. So what are we saying? If I'm going with the Bayes theorem, it has to be like the probability of age is less than 30 given a default has occurred, multiplied by probability that the default has occurred, divided by the probability of the age is less than 30. This is what is the Bayes theorem saying. So we already know age less than 30 given defaulted 3 out of 10. 3 out of 10 is the age less than 30 given defaulted, multiplied by probability of default occurring, which is 10 by 40. And I divide that entire thing by probability of age less than 30, which is 5 by 40. So overall, what is being said is 3 by 5. So the probability that a default will occur for a person who is less than 30 is again 60%. And similarly, the probability of no default will occur given a person is less than 30. Obviously, we know in that case, again, if I work it out like this, the same way, probability that less than 30, age less than 30, given no default, multiplied by probability of no default, divided by probability of age less than 30. If I do this, obviously I'll end up at 0.4. So obviously, for a below 30%, the probability of yes is much higher and the probability of no is much lower. So your final decision will be that this particular person will default. So that is how you are taking a call on whether a particular person will default or not. So you can very well keep applying this kind of mechanisms across, right? So same way, you can even go for, let's say, what is the probability of, you can actually bring in multiple variables also, right? Just like the age, you can also bring in one more dimension. So what we are saying is, we simply find out what is the probability of default and what is the probability of non-defaulting given each of the features and all the features working together. So obviously, as we have said, because there is no modeling and all, it's a simple arithmetical calculation. You will always find that it's a very, very fast execution. Even if you have a large volume of the data, probably doing the calculations is very, very simple. So you can use this not only for binary classification, you can very well use it for the multi-class classifications as well. So mostly in a text where the number of columns is much higher, which means it's a very high dimensional kind of a data, you will always find the applications of the naive Bayes coming in there. And probably you can use it in credit scoring also, as we are using right now, or probably any other classification problems, you can very well think of using the naive Bayes. Now, the only thing here in the naive Bayes, there are different models associated with the naive Bayes. Slightly differing here. The different models. So basically, you can look at them as a Gaussian naive Bayes, or you can think of a multinomial naive Bayes, or a Bernoulli kind of a naive Bayes. Now, all these are directly associated with the feature variables. So you have to look at what are your typical feature variables, and based on that, you have to initiate that particular naive Bayes model. When you are working in the practitioner's world using Python and all. So depending on the kind of features, you will choose the appropriate naive Bayes model. So for example, if you are talking about the Gaussian naive Bayes model, so obviously it assumes that all the features, they follow a kind of a normal distribution. So this is again one more aspect. So it assumes that all the features follow a normal distribution. So most of the features should be continuous. So you can't have binary variables and all there. So you should have mostly the continuous variable, and they are completely following a kind of a normal distribution. This is for Gaussian naive Bayes kind of an algorithm. Whereas when we are talking about the multinomial naive Bayes algorithm, so we will say that the data is multinomial distributed. The distribution of the data is a multinomial distribution. So especially when we are having text and classification of the text, you can very well, because there are multiple categories that can typically come up. Right? So if there are multiple categories in the data, then probably you can very well use a multinomial kind of a naive Bayes algorithm. Otherwise, we can talk about a Bernoulli naive Bayes, right? But so the observation, the features, the predictor variables or the feature variables, they are primarily binary or Boolean variables. When your features are primarily binary, we'll use this. When the features are categorical, but multiple categories, not just binary, right? Multiple categories, then you can use a multinomial naive Bayes. If the features are all binary categorical, like you have already converted them into dummy variables, in that case, you can very well use the Bernoulli naive Bayes. Okay. So this is also one more, I mean, when that is when you are actually initiating a scikit-learn model, you will have all these options on the scikit-learn model. You will have to simply choose that specific option. So if I go back to my data to really test that out. So you see here I am taking Gaussian naive Bayes because majority of my variables are, we have already done the box calls or EO Johnson transformation on the data, right? We have done a lot of pre-processing, which means the data has already come more and more closer to being normally distributed. So that's the reason we are going for a Gaussian naive Bayes model. So you can very well predict it on the testing data. You can look out for the accuracy on the testing data. Obviously, it looks like the accuracy is not that great. Right, probably here the accuracy is hardly 81%, slightly below that of the other model. Then you can, you don't have too much of hyperparameters here, because as you see, it's a very straightforward arithmetic calculations, very little assumptions regarding the execution of the model. So that's the reason you don't need to get into the hyperparameter tuning, etc. for this naive-based model. Okay. So I think with this, majority of the models, we have come to an end. So this multi-layer perceptron, I will discuss probably in the next class. Obviously, this multi-layer perceptron will become the basis for the deep learning, right? I'll introduce one session of each of these things. The additional aspects we are discussing only one session of each of them. So probably I will do the clustering part also, and after that we will get into all this. So the algorithms, the various machine learning algorithms we have discussed from the perspective of classification. The same kind of mechanism you can adopt for regression also. So what I'll do is I'll share one such kind of a file. We will not discuss the regression problem in the class because it's exactly the same. The only thing is, instead of using MLP classifier or instead of using naive-based, not naive-based, the random forest classifier, we'll use random forest regressor. Instead of using decision tree classifier, we'll use decision tree regressor. So I'll quickly, otherwise in one class, I'll try to walk through the entire regression model, right? And I think after that, we'll move on to the clustering aspect. So we are almost coming to the end of the classification problems. We had a great discussion, deeper discussion in terms of how each of these models work in the real world and what is the mathematics to some extent, definitely. We have not derived all these things. So major focus being the practitioner's perspective, but at the same time, a conceptual understanding as well. So we will look at this ANN, which is the multi-layered perceptron, and then we will move on to the regression models. We'll quickly walk through the entire regression model, and then we'll move on to the clustering algorithm. Or probably we can take up clustering initially, and then towards the end we can run this regression. First, I'll share the regression code with you. Right, I will do like that. I'll take up one use case for regression also. I'll share the regression code with you. CART is nothing but decision tree. Right, CART is a decision tree, Madhav Kumar. It's actually called classification and regression tree. CART is nothing but, it stands for classification and regression tree, which is nothing but a decision tree. So there are different different algorithms within the decision tree. So CART is one such kind of an algorithm. But overall, it is a model-wise, it's a decision tree model. Okay. All right, then we'll stop it here for today. We'll have one class on Monday. Right, probably there we'll try to finish off this classification, and we might start off the clustering. Right, the regression models, which is exactly a copy of classification. The only thing is your target variable is a numerical variable. So I'll share the code with one use case for different models. And in case you have specific questions, we'll discuss them. Otherwise, it could be a self-learning as well. All right. So yeah, if there are questions, fine. Otherwise, I'll stop it here. Thank you everyone for listening to this session. We'll again catch up